Bismillahirrahmanirrahim. Assalamu alaikum dear students. I am Arif and I welcome you all to the next session on the subject of system programming with Linux. The title of today's session is Exploiting Buffer Overflow Vulnerability, Part 1. I think I will be able to close this topic in a total of 3 sessions inshallah. This slide shows the agenda of today's session. We will start with the concept of buffer overflow vulnerability and how it can be exploited. I will also talk about various exploit mitigation techniques. Since I assume that the vulnerable programs are running on x86 64-bit architecture, so I will have a quick recap of the hardware architecture and its assembly first. Moreover, since stack-based buffer overflow has a lot to do with functions activation records and the platform's function calling convention, so I'll do a bit of scuba diving in this part of the ocean as well. For the proof of these concepts, I will be using the all-time famous GNU GDB debugger. To enhance the firepower of GDB for analyzing, exploiting, and doing reverse engineering on executables, I will be using a GDB plugin called PEDA, Python Exploit Development Assistance for GDB. Okay dear friends, we have a lot to learn, so let's start playing. Okay, first of all, let me talk about certain terms. Cybersecurity, which encompasses all the techniques for protecting computers, networks, programs, and data from unauthorized access or attacks that are aimed for exploitation. A vulnerability, which is a flaw or weakness in a system design, implementation, or security procedure that could be exploited, resulting in notable damage. Example of a vulnerability is a house with a weak lock on the main door. The other term is exploit, which is a software that take advantage of a vulnerability leading to privilege escalation on the target. Example of an exploit is the duplicate key with the robber using which he or she can enter the house. The other important term is payload. A payload is actual code or software which runs on the compromised system after exploitation. Example is the task that the robber will perform inside the house, that is stealing jewelry and cash. Well, this slide shows a brief list of the types of vulnerabilities that compromise integrity, availability, and confidentiality. And this list grows larger every year. The vulnerability we are going to talk about today is buffer overflow. Well, let me move on to the Linux terminal and show you an example. Okay, so if you see this code, this is a very simple code. Inside the main function, if no command line arguments are passed, it displays the message no command line received and exit. And if argc is greater than 1, that is some command line argument is passed to the main, then the first command line argument is passed to this function f1. It is assumed that the command line argument is a string, and this function f1 actually uses strcpy function to copy this string into this buffer of size 10. It finally prints that string on the std out and returns to main. Let us compile this piece of code with ggdb option to enable debugging, stack overflow.c. Let me run it without any argument. Let me run it with some number of A's, and let me run it with lot of A's. So once I pass it more number of A's, it print them on screen and then it says segmentation fault, a code dump. How many number of A's we need to pass for this program to be crashed? Let me count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and 17. So I have passed 17 A's, it has not crashed, and if I pass 18 A's, the program crash. Okay, so let me load this code file as well as this executable to find out the reason. And it says the segmentation violation code is generated and signal is passed, and the error is because of this line. Let me open this program in Vim, stack overflow.c. So we all know that the problem is because of this function strcpy, because strcpy do not do bound checking. So when a user gives more data, it overflow the variable buff. So let me use strncpy instead, which do the bound checking as well. Let me save and exit the program, compile it again, and now let me run it with, and let me pass it a string using python -c print. Let me pass A's. How many A's? Let's suppose 500 A's. Okay, and it will not crash. It will not crash at all because we have now used strncpy. Let's fall back to the slides. You have seen the practical example of a program which suffers with the buffer overflow vulnerability. So a buffer overflow is a bug in a program which occurs when more data is written to a block of memory than it can handle. The first published paper on this vulnerability came from L.Summary with the title of Smashing the Stack for Fun and Profit. I have mentioned two links. Please, these are a must read. Well, dear friends, buffer overflow exploit was first used by Morris Worm in 1988, followed by Code Red Worm in 2001, and then Slammer Worm in 2003. The buffer overflow is still one of the top vulnerabilities. Hackers mostly use buffer overflows to corrupt the execution stack of a web app. By transferring fully crafted input into a web app, a hacker can make the web app to execute arbitrary code and probably take over the server. And this is what we are going to do in these sessions. Well, this illustration will describe the concept of a stack-based buffer overflow at an abstract level. Well, consider this piece of code in which main function is calling function f1, and this f1 function creates a buffer of about 48 bytes. Then it uses the getAs function to input characters from the keyboard. Then it print those characters on standard output, and finally control falls back to the main function. This is the function stack frame or activation record of function f1, containing the function parameters, if any, the return address to the main function, the base pointer of main, maybe some alignment space, and then 48 bytes memory allocated for the buffer. Well, remember, dear students, the stack grows downwards. Rather, let me say, stack grows from higher address to lower addresses. And once we create a character variable, array like this buff, the data written in it will move upward, that is from low address to the higher address. Now let us suppose that the user starts entering data. It starts entering data which is written inside the buffer. But instead of writing just 48 characters, it enters, he or she enters more characters in the array, which start overwriting the existing contents of the stack. And finally, they may overwrite the return address as well. Once the program will try to execute this instruction now, the return instruction, it will try to return to this address. and which is an invalid address right now. If I read it in hex, it is 41414141, and which might not be the address of executable page inside the code section. So that is why you get the signal segmentation violation. Let us now try to understand how can we exploit this vulnerability. Well, dear students, all a hacker need to do is, instead of lot of A's, inject a list of carefully crafted machine instructions for that specific platform. And normally we call this the shellcode. The other thing hacker need to do is replace this return address saved on the stack with the starting address of where this shellcode is residing. And when this shellcode execute, you may get a root shell on that machine. Well, this is what a classic stack-based buffer overflow exploit is. And this is a place in the ocean of hacking where we are going to do a scuba diving in today's and upcoming sessions. Dear students, before I proceed, let me tell you that there are a lot of security protection mechanisms in place these days that protect our system from this traditional or classic stack-based buffer overflow attack. The first is the NX bit, that is known executable bit. Well, these days the process stack, heap and data section are all known executable, and the text section is known writable. Since in this case we need our stack to be executable, so if the stack is non-executable, this exploit or this shellcode will not execute. Since we are newbies in this field, so we will instruct GCC to disable the non-executable bit in the page table entries of the process stack. So we will compile our program with this option -z exec stack. This will make the stack executable. The second protection mechanism is the stack canary. A stack canary is a known value or word that is placed just before the return address. Suppose we have the return address over here, the stack canary, a known word is written over here. A copy of this word is saved somewhere else as well. And before the hacker overwrites the return address, the canary will also be overwritten. As you can see, the E is over here. When a function call returns, this canary value is checked to make sure that the stack copy agrees with the saved elsewhere copy. A mismatch indicates that the stack is overwritten. Once again, being newbies, we will use the option -fno-stack-protector to compile our programs to ensure that the stack canaries are not used. The third protection mechanism is ASLR, address space layout randomization. This is an operating system based defense. ASLR randomizes the addresses of stack, heap and shared library section in a process address space. Every time a program executes, it is given different addresses, thus preventing an attacker from reliably jumping to an exploited function in memory. On Linux systems, ASLR can be disabled by writing a 0 in this file. You can use this command to disable the randomization. Proc sys kernel, and the file name is randomize va space. Another security protection mechanism is PI, position independent executable. PI executables are executable binary made entirely from position independent code. And PI binaries along with ASLR prevent attackers from knowing where existing executable code is during an attack like, for example, return to libc. Once again, being newbies, we will try to have compile our program with -no-pi option. And the last is fortify source. It is a macro that detects buffer overflows in function like strcpy, strcat, getas, memcopy, sprintf, and so on. If your program statically copies a larger string in a small buffer, it gives you the warning during compilation. And if your program assigns a larger string to a small buffer during runtime, as we have just seen, it will raise a buffer overflow exception along with maybe the segmentation violation as well. Always try to compile your program with -d_45_source macro, and this macro works only if the optimization is greater than 1. So you need to give -o2 over here if you want to use this macro. Well, last but not least, none of these mitigation techniques is completely foolproof, so they all can be violated. Okay, my dear students, to have a strong grip on the topic of buffer overflow, you need to know a bit about the Intel architecture and its assembly as well. Let me spend a few minutes and have a quick recap. Well, there are 16 64-bit general purpose registers, and we can access their lower 3216 as well as 8 bits. Their names are mentioned in the table. Related to stack, there are two very important registers. First is the RSP, the stack pointer, which is used to point the current top of the stack. The other is RBP, the base pointer or the frame pointer, and always points to a fixed location within a frame. All the local variables and parameters within a frame are referenced by giving their offset from RBP. There is another important register, RIP, which is not shown over here. This is the instruction pointer that stores the address of the next instruction to be executed. Other than the general purpose register, we have the code segment registers. There are 6 16-bit segment registers. Each of the segment registers is associated with one of the types of storage, the code, data, or stack. The CS register in particular contains a segment selector for the code segment. SS register contains the segment selector for the stack segment. The DS, ES, FS, and GS register point to 4 data segments. And the availability of 4 data segments permits efficient and secure access to different types of data structures. You can see the details in some assembly book. Well, we have the flags register, R flags. Right now it is having 64 bits, but most of them are unused. The most commonly used flags are the status flag, like the carry flag, parity flag, auxiliary flag, zero flag, sign flag, and overflow flag. They all have specific bit positions. For example, the bit position of carry flag is 0, and the bit 0 is set if the previous operation resulted in a carry or a borrow out of the most significant bit of the result. And you all must be knowing that the Intel architecture is little endian, and by little endian I mean the lower order byte of the number is stored in memory at the lowest address, and the higher order byte of the same number is stored at the highest address. And if you store 1 in a little endian machine, you see the lower order byte is stored at the lower address. Well, this slide shows a summary of different categories of Intel assembly instruction. Important for today's session are the instructions that transfer the control of execution. For example, the jump instructions, which are like unconditional goto. The branch instructions are go to some address if the last operation had some flag set, for example the 0 flag maybe. The calls or the call instruction is an unconditional goto that pushes the next instruction address on the stack before transferring the control. And finally, the ret instruction or the return instruction pop that address from the stack and control transfer back to the callee. Oh well, dear students, this slide shows a comparison between a C program, its corresponding assembly in Intel format, and the machine language. These are the opcodes related to this high level language, and these are the assembly mnemonics. Okay, let us move on to the Kali terminal and have a quick view of these concepts. Let me clear screen. Let me cat prog1.c. Well, this is a very basic C program that uses the famous printf function of the standard C library to print a string on the screen. Prog1.c. And of course it has returned 26, which is the count of the number of characters printed. Let us clear screen and see another program, prog2.c. Well, this is another C program that performs the same functionality, but it uses a C library wrapper of the write system call, and we all have seen its uses. Let me compile it. Let me execute it. Let's check the exit status. Great. Let us see another program, prog3.c. Well, this program again performs the same functionality but uses the syscall system call instead of the C library wrapper. And this is a system call number of write, of course. And this is a syscall, and this is a system call number of exit. Let me compile this program, execute it. So that's great. Let us see some programs in x86-64 assembly as well. prog4.nesum. Why? Well, this assembly program calls a standard C library function puts and exit. Note that the only argument to puts and exit are placed in this register RDI. Also note the extern keywords used to declare the two symbols puts and exit. So it's simple. I will be using the net-wide assembler for assembling this code. You can use FASM, the FAT assembler, or GAS, that is the GNU assembler. If you are on Microsoft platform, you can use MESM or TASM, turbo assembler. Let me use net-wide assembler, NASM, ELF64 prog4.nesum. So this will create the .o file. Let me use GCC to do a linking of prog4.o with the standard C library, and let me execute it. Oops. Well, yes. We have to create a known position independent executable in case of dynamic linking. So let me use -no-pi to create a known position independent executable, prog4.o, and this time we will be able to execute it successfully. So that's great. Let us see another assembly program, prog5.nesum. Well, over here, instead of using the C library function, we are using the syscall. Note the system call number is placed in the register RAX. 1 is the system call number of write call, and the arguments to the write system call are placed in RDI, RSI, and RDX. And similarly over here as well, we are calling the exit system call, and we are placing the argument to the exit system call in RDI and the number of the exit system call in RAX. I think we have seen these codes before as well in probably the second video lecture, -ELF64 prog5.nesum. Oops, nesum, NASM. Sorry for the typo. Let me link prog5.o and let's execute it. So that's work. I think enough of C and assembly programming. Let us fall back to the slides. Okay, well, to really understand the concept of buffer overflow and to exploit programs having this vulnerability, we must have a very clear understanding of the function calling convention of the architecture on which the vulnerable program is executing. In our case, it is x86-64. Well, this is the logical layout of a process address space. We have seen it many a times. Let me just touch upon the stack. Well, this stack is at the top of the memory below the kernel at higher addresses. It grows from higher memory address to lower memory addresses in all the architectures, including MIPS, Motorola, as well as Spark. In our case, all the push and pop on the stack will be 8 bytes. The stack width will be 8 byte. And whenever a new function will be called, a new function stack frame or activation record will be created over here. Let's move ahead. Well, dear students, a function stack frame or activation record is pushed or created on the stack when a function is called, and popped or removed from the stack when a function returns. Function calling convention means how the function arguments are passed, in which order the function arguments are passed, who is responsible for creating the FSF, and who is responsible for unwinding the FSF. On x86-64, the first 6 integer or pointer arguments are passed via registers RDI, RSI, RDX, RCX, R8 and R9. Any floating point values are passed in registers XMM0, XMM1, XMM2 and so on. In case if more than 6 arguments are passed to the function, the 7th argument onward are passed via stack. And remember, the function return value is also placed inside register RAX. Let us now understand how a function stack frame is created. Right now the main function is executing, suppose, and this is the function stack frame of main function. Note the register RBP is containing the address of the start of the function stack frame, while RSP register is containing the address of the last address of this function stack frame. Suppose the main function calls another function f1. Before the control goes to function f1, the code inside main perform following 2 tasks. The first is, it places the function arguments in 6 registers RDI, RSI, RDX, RCX, R8 and R9, and the rest, if any, are pushed on the stack in reverse order. The contents of return address is also pushed on the stack. Then the control shift to the called function f1, which performs a procedure prologue. The first instruction of procedure prologue is push RBP. That is, this address is saved inside the stack over here. And then we move RBP to where RSP is pointing. So RBP from here is moved to where RSP is pointing. Move RBP, RSP. And finally, move RSP down. From here, RSP is moved down below the stack. We have subtracted 0x20 from RSP to create space for the local variables for function f1. Now you can see the function stack frame for f1 function is in place with register RBP pointing to its base address and register RSP pointing to the top of the function stack frame of this function f1. After function f1 is done with its execution, it finally calls the return statement to return the control to the main function and clean up its function stack. We say it performs procedure epilogue. The first instruction of this procedure epilogue is the leave instruction. The leave instruction, which does not have any operand, reverses the action of previous enter instruction, and it is done in 2 assembly instructions. First is move RSP, RBP, that is, move RSP to where RBP is pointing and clear the space of the local variables. You see? The second is pop RBP, The pop RBP instruction will move RBP to its old location. So this RBP will move to its old location over here, whose address is stored on the stack like this. Finally, we have the ret instruction. The ret instruction simply do a pop RIP. That is, this saved return address is placed inside the RIP register. It also removes any function arguments on the stack, if any. Now you can see the function stack frame of F1 is completely removed from the stack, and the control of execution is there inside the main function. Okay, well, this slide shows the function stack frame of this function F1, which is passed 8 arguments, 6 via registers RDI, RSI, RDX, RCX, R8 and R9, and the remaining 2 via stack, pushed from right to left. H is pushed first and then G is pushed. After the arguments, you can see the return address, base pointer, maybe some alignment space, and then space for the local variables. Well, this red zone at the bottom of the stack can be used for a leave function, in which case there is no need for adjusting the RSP and RBP. And this is done only if the program is compiled for optimization. Let's move ahead. Okay, so for proof of concept, ladies and gentlemen, we are using GDB. There is a long list of debugging and reverse engineering tools that can be used to debug, decompile, disassemble, and analyze binaries. They are like Hopper, EDB, IDA Pro, Radar 2. We will be using GDB. GDB is too good a debugger, however it lacks intuitive interface. It do not have a smart context display, do not have commands for exploit development. So we will be using PEDA, Python Exploit Development Assistance, which is a plugin for GDB, used extensively in exploit development. It is supported by GDB 7, version 7 onward, and Python 2.6 plus. So let us now move on to the Linux terminal and see a program as a proof of our concept. I assume that you all already have a working knowledge of GNU GDB debugger. If not, please visit this link and watch my video on GNU GDB. Let us clear screen. Well, to have a better display about the contents of the register stack and assembly code while debugging, we need to install PEDA plugin. Let me check out my GDB version first. It is 7.12, fine. Python version is 2.7, that is fine. If you do not have Python installed, do install Python first. Well, dear students, you can download the PEDA from its official GitHub repository or from the class Bitbucket account using this git clone command, https bitbucket.org Arif PUCIT PEDA.git, and let me copy it to our directory in my home directory, that is PEDA. So that directory already exists. Let me say PEDA1. So it is done. Okay. So this will download all the required Python files in that particular directory. The next task you need to do is to modify the GDB init file inside your home directory, so that whenever you run GDB, the PEDA plugin also gets started. And for that you need to give this, have this line in that file, source PEDA dot py, and we need to write or append this inside this GDB init file. You can check that out, confirm it. So this line is there in that file. Now let us run GDB, and you see we have a different prompt now, gdb-pda $. So instead of GDB prompt, you see this prompt, and whenever you see this prompt, that means we are running GDB under PEDA. Well, dear friends, you have seen how we can get help about GDB. By just writing help, we get a list of different classes in which GDB commands are categorized. For example, if I write help running, which is a class of command, we get a list of single line description of all the commands in the running class. And if I get help about SI, so I know that SI is for stepping in the assembly code. Similarly, you can get help about PEDA. So single line description of PEDA subcommands. There are a lot of commands, for example, help ASLR. So this will tell you whether the ASLR is on or off. Let me check out. It is off. You can check out for security options. For example, on a.out, let me check out. Canary is disabled, Fortify disabled, NX disabled, Pi enabled. Okay, fine. You can have get PID. So you can get the commands, and you can get help, and you can read it. And whenever you are going to pursue these, please make sure that you disable the address space layout randomization. We have already seen that it is already disabled, but just to write down the command for you, you can do it like this. You need to write to this file proc sys kernel nel randomize underscore va underscore space. Oops. I'm inside PEDA. I shouldn't have done it over here. Echo 0 pipe it to sudo t, and the file name is proc sys kernel and randomize va space. So it is 0 now, so it's fine. Now let me show you a function which we are going to use to understand the concept of function calling and the concept of growing of the stack and the shrinking of the stack. Function calling.c. Well, okay. So the main function is creating two long variables, var1 and var2, and a character pointer str2 containing Arif. Then it is calling this function f1 and passing 8 parameters to it. Over here inside the function f1, we are receiving the 8 parameters, and this function f1 is creating two local variables, var1 and var2, and then it is calling a function f2 and passing only one value to it, and that is 5. This function f2 is a leaf function, as it is not calling any other function and is finally returning a value b, which will be containing, of course, 6 to function f1, which is returning 1 to main function, and finally main is returning 0 to its parent over here. Let's compile this program and load it in GDB. Let me clear screen first. gcc-g gdb function calling.c -o function calling. Okay, let me run GDB in quiet mode, function underscore calling. Okay, so reading symbol is done. Let me pdis use this command, disassemble main with a p. Let me shrink the size a bit. Let me clear screen and done it again. Shrink more. Okay. So this is the disassembly of main. You can note the procedure prologue over here. This is the procedure prologue. Note the call instruction to F1, and finally here is the procedure epilogue, the leave and the ret instruction. Let me show you the summary of F1 as well. Over here as well, this is the procedure prologue. This is the call to function F2, and this is the procedure epilogue. Let me show you the summary of F2. This is the procedure prologue. Being the leave function, you see it is not using the subtract instruction for local variables, and will be using the red zone for the local variable. And over here we have the procedure epilogue. Let us apply a breakpoint and run the program. Break main, and let me run it. Okay. Since we are using PEDA, so there are 4 sections of the output. The first section over here shows you the general purpose register, including the flags register as well as I think the RIP as well. Yes. Below the registers we have the code section. This is the code section, part of the assembly with the current instruction highlighted in green with the arrow at the left. This is where the RIP is pointing, 4668. You see 4668. And the third section is the stack. We know Intel stack grows towards smaller addresses, and this stack also grows towards smaller addresses. Remember, this is E1C8, E1C0, E1B8, E1B0. The stack is growing upwards towards smaller addresses. And finally over here we have the last section showing you some messages and the C instructions being executed. Let us step into the assembly instructions one by one by pressing SI. You see right now I am on this instruction, and if I just press enter, I keep on moving ahead, and you see what is happening. Let me show you the code over here as well. Let me show you the code of this program, function calling.c. The first instruction is we are creating the local variable containing 1, 1, 2, 2, 3, 3, 4, 4 and so on. And you see this variable has been created over here. And now this instruction is being executed. That is, the second variable is being created, and this will be created over here. You see, this is the first local variable, this is the second local variable. And after this, if I come up over here, this is the C instruction which is going to be executed now, shown over here. So this will be created. This will be pointing to string Arif over here. And now the function F1 needs to be called. You see over here in the high level instruction, this function needs to be called. But before the control actually transfer, the 8th and the 7th argument are pushed on the stack first. This argument and this argument will be pushed on the stack. Let's see this. You see, these 2 arguments are pushed on the stack. And after this, if you see over here inside the assembly, the remaining 6 arguments will be placed inside the registers. So let me move. And now you see all the 6 instructions have passed, and if I come up over here, you can see the first argument is in RDI, second is in RSI, third in RDX, fourth in RCX, fifth in R8, and sixth in R9. So this is the state of the stack, and now we are going to call F1, and once F1 will return, this is the return address on which it will return, that is 546C6. And if I press enter, this address will be pushed on the stack over here. You see, This return address is pushed on the stack over here, 46C6. And now if you see, the control is inside the F1 function. And the first three instructions of F1 function are the procedure prologue. These are the procedure prologue, creating function stack frame for F1. Let me press SI, let me press SI, let me press SI. Now the two arguments, the 7th and the 8th argument are already on the stack, and the remaining 6 are now moved from the registers to the stack. These arguments are there in the registers, now they are moved on to the stack. You see, 2, 3, 4, 5 and 6. And after this, the two local variables will be created. Remember, we are executing over here now. These two local variables will be created, variable 1 and this variable 2 as well. But you cannot see them over here, these two local variables. The variables were 1, 2, 3, 4, 5, 6, 7, 8, 9 and 0, A, B, C, D, E, F. They have been created. Let me show you, because they are below the stack somewhere over here. Let me use a command to display the contents of the memory. This, let me copy this, RBP minus 0x8. This will be containing the first variable. Well, yes, 1, 2, 3, 4, 5, 6, 7, 8, 9. And this will be containing the other variable. Remember, all addresses are related to RBP. Yes, A, B, C, D, E, F. So that is great. Now this function F2 needs to be called from function F1. So this is function F1, and this function F1 is going to call function F2. And once it calls F2, it needs to pass the parameter to that function. The only parameter will be passed via EDI, and that only parameter is 5. So let me press SI again. EDI will be containing 5 now. You can check that. EDI, RDI contains 5, one and the same thing. And now once we call this function, this is the return address 464F. This will be placed onto the stack. You see, 464F. This return address is placed on the stack, and the control is there inside the function F2. F2 function is the leave function, so inside the procedure prologue there is no subtract instruction, as it will execute in the red zone of the stack. Let me keep pressing SI and move ahead, keep moving ahead, and finally you see we have reached the procedure epilogue of F2. The return value of F2 is placed in EAX. If I move up, probably I have said before that the return value will be 6, and yes, it is 6. This value has been placed. Now we are going to call the pop instruction, and then we are going to call the ret instruction. Once we call the ret instruction, remember this is the top of the stack, which contains the return address, that is 5464F. This is the return address to F1 function. And you see, we have fall back to 464F, the next instruction after the call inside F1. Let's move ahead. And now we have again the leave and the ret instruction of F1. This is a procedure epilogue. If I move ahead, after the leave again, you see at the top of the stack we have the return address, and that is 546C6, and this is the address of the main. So the control will move to this place now, 546C6, the main function. So finally we are back in the main function. It also places its return value in RAX or EAX, and then it will call leaf and call ret. Let's press C to continue now, and the process exited normally. Let us press Q to quit GDB. Okay, now dear students, we have a fair idea of the working of stack as well as GDB with PEDA, just for these different portions of the output that it shows you. Let us now once again run the Stack Overflow program. Stack overflow.c, and let me make the vulnerability again over here by removing the strncpy function with strcpy. So let me compile gcc-ggdb stack overflow.c-o stack overflow. Let's load this in quiet mode. Stack overflow. It's done. Let me see the disassembly of let's suppose main first. Well, you can see if argc is greater than 1, then it calls function f1. The code moves over here. The function f1 is called. Otherwise, the code will jump to this place. Yes, this place, the puts function, which will just print no command line argument. Well, fine. This is the procedure prologue and this is the epilogue. Let me show you the summary of function f1 as well. Well, it uses strcpy function to copy the string to buffer and then print the string on screen and finally returns to main. Let me show you the C code over here as well for better understanding. Stack overflow.c. So this is the code which I have just described it assembly over here. Fine, let's apply the breakpoint on main and let us run, and let me pass it a string of 20 A's. Python -c, use the print capital A's. How many? I think 20 will be enough. Fine. So let me confirm. Print argc. So it contains two arguments. Print arg v sub 1, and it contains a 20 times. Well, fine. The input to the program is correct. Let me use si now. Fine. Since argc is greater than 1, so the sequence of execution will move to call the f1 function. Let me press it again, and you can see the control has moved to this path. And before control shift to function f1, you see that the arguments are passed via RDI. Let me move ahead. Well, fine. This is the return address which will be saved over here now, because we need to fall back. That is 477C. This 477C is saved in FE188. So this is the stack address and this is the return address. And now we are in function f1. Function f1 executes. Let me keep on pressing SI. And let me reach to the strcpy function, and before that let me press NI. I don't want to jump into the code of strcpy. Well, this strcpy function will copy 20 A's in the buffer of size 10, and it will start from the address E170 and to higher addresses till FE188. And this is the address which contains the return address. So this strcpy function will start writing the buffer from here and keep moving towards the higher addresses, and I think since they are 20, so it will overwrite this return address as well. Let's check out. And you see FE188, which contains the return address ending with 477C, now contains 4141 at the end. So the return address is corrupted. Okay, so let me press NI again and move ahead and move ahead and move ahead. Now we are at the printf function. Of course, this line will be printed, and then we will move on to the leave and the ret instruction. And once we reach the ret instruction, you see this is the address now where we are hitting. Our IP contains this address, and if I press continue, you will see we have received the SIG-SEG-V, because this return address is probably of some location which is not in the code section and might not be having even execute permissions. Okay, let me quit. Let's fall back to slides. So we are done with this Stack Overflow part as well. Okay, so modifying the function return address. Okay, dear students, we have seen how the return address stored on the stack gets corrupted due to buffer overflow. Let us now see how can we modify the return address to some address of our own choice. Consider this piece of code in which the main function over here is calling function f1. The function f1 is calling function f2. The function f2 is calling function f3, and this function f3 is returning. Over here as well, you can see the activation records of all the 3 functions or 4 functions on the process stack. Function stack frame of main, then f1, then f2, and then f3. In all this piece of code, you can observe there is a function named virus, which is not called from anywhere in the program. Let us see how we can call this function virus while the program is in execution. Let us move again to the Linux terminal and see this in action. Let me clear screen. Let me show you the code cat virus.c. So this is the same piece of code. Just note that this function virus is not called anywhere in the function. So anyone can say that this will not execute. Let me compile gcc-ggdb virus.c with the name of virus, gdb-q virus. Let me put a break at main and let me run. There we go. Okay, see the code section. We are inside the main function, and let us see the disassembly of virus, PDISASS virus. And for the time being, just let me copy the address of the first instruction of this this function virus. And let me clear and let me step into the code. So we are inside the main function, and we are going to call the f1 function. And of course, the next instruction, that is 6c1, the next instruction address will be pushed onto the stack. Note this out. Okay, now we are inside the f1 function, and we are moving and we are moving. And now once we will be calling f2 function, this address will be pushed onto the stack, 46b0. Note that out, 46b0. So this goes ahead. Let's change the contents of register RIP. Let me say that set $RIP is equal to, and let me paste the address of the virus function over here, and let me confirm print $RIP. So it contains the address of the virus function, the first address of the virus function. Let us move ahead. Let me press SI. Note that the control is right now inside the F2 function. I press on to the next instruction. It will not go to this instruction 692. Rather, it will move to the first instruction of the virus function. Let me press C and it will continue. And you see, this line which is there inside the virus function is executed and displayed on output. Let us hack planet Earth with Arif Bhatt. That is great. Let us fall back to the slides. Okay, so dear students, that is the end of today's session. Well, today I have tried to build a foundation, just a foundation, basing on which in the next sessions we are going to exploit different vulnerable programs suffering with the stack-based buffer overflow vulnerability. Today we have used PEDA, and in the next session, inshallah, we will use a Metasploit framework as well for writing, testing and using exploit code as well as the shell code. Hope today's session was informative for you all. If you have liked it, please subscribe my YouTube channel and share it with your friends. Wish you all the best. Happy learning and Allah Hafiz.